Hello and welcome to Vodcast 2.2. In this Vodcast, we're going to build off of our general knowledge of the rock cycle and talk specifically about igneous rock. Here's the picture that we went over in extensive detail in the last Vodcast. In this particular video, we are only really focused with the top portion of this picture, and it's this purple arrow, the cooling and crystallization arrow, that takes us from molten hot liquid rock to the igneous rock that is the focus of our conversation. Let's start off with some definitions. Igneous rock forms when either magma or lava cool and crystallize. Magma typically originates by melting in Earth's mantle, and remember, for us to call it magma, it must be molten hot liquid rock below Earth's surface. Lava is also molten hot liquid rock that's at extremely high temperatures, but lava is magma that has reached Earth's surface. In describing the mechanism for how magma makes it to Earth's surface to form rocks in the first place, there's a really important concept that's going to come up over and over in this course. Warm stuff tends to rise. That hot liquid rock that's generated by melting in the mantle is less dense than the surrounding rock. And remember in a previous vodcast how I talked about ice floating because it's less dense than water? Well, if magma is less dense than the surrounding rock, the magma will rise just as the ice cubes would float to the top if I were to shake that water bottle. On the screen, I've shown another picture of perhaps my favorite igneous rock, granite. Granite is a coarse-grained igneous rock. The three primary minerals, as I've mentioned in previous videos, are quartz, hornblende, and feldspar. And we're going to come back to granite in a moment when we talk about how cooling rate affects the size of mineral crystals in rocks. This is a pretty important image. And before we start talking about what Bowen's reaction series tells us, we have to know that magma has a very complex chemistry. It's not a pure substance like water. We know that water would go from a liquid to a solid at 32 degrees Fahrenheit or 0 degrees Celsius. Water doesn't freeze over a very, very large temperature range from say 50 degrees down to negative 20 degrees. It freezes at a pretty specific temperature. But magma, with its diverse chemistry, has a lot of stuff in it. And as the magma cools, certain minerals will crystallize out over specific temperature ranges. So let's take a look at the temperature range for this image. At the highest temperature, we're talking 1200 degrees Celsius. And at the lowest temperature, we're talking 750 degrees Celsius. Quite frankly, you can't even comprehend how hot we're talking, because in our everyday lives, we don't see temperatures this high. Even the best ovens can't come anywhere close to reaching the temperatures that we're talking about right now. But towards the top portion of this image, we're talking about the highest temperatures. And as you work your way from top to bottom, it's important to realize that the temperature is decreasing. Okay, let's talk about what this picture tells us. The arrow you see closest to the top of this image is the arrow for olivine. Olivine will be the first mineral to crystallize for this cooling magma. What that means is the formation of solid olivine crystals will start to occur, while the rest of the minerals talked about in this particular image are still in their molten liquid state. Take a look to the far right side of the diagram. Plagioclase feldspars crystallize over an extremely wide range of temperatures. In fact, the crystallization for plagioclase feldspar minerals starts just a little bit below the temperature in which olivine starts to crystallize, and the crystallization continues all the way into the felsic region. Your calcium-rich feldspars will crystallize at higher temperatures, and the sodium-rich plagioclase feldspars will crystallize at lower temperatures. If we focus on the mica family, you'll notice that biotite crystals out at a higher temperature than muscovite. And our mineral constituents of granite, specifically in this image, your feldspar and quartz, don't begin forming solid crystals until you've reached a relatively low temperature. Another important concept to consider in this image is that because olivine crystallizes out at such a high temperature and over a relatively short temperature range, while quartz crystallizes out at a much lower temperature, you don't typically find igneous rocks that contain both olivine and quartz. However, those minerals that do tend to crystallize out at similar or even equivalent temperatures are typically found together in igneous rock. Granite rock contains feldspar and quartz because feldspar and quartz tend to crystallize at roughly the same temperature. Our last consideration in this vodcast is how cooling rate affects rock texture. Shown on the screen are 6 different rock textures, but the 3 that I'm going to focus on for this discussion are glassy texture, coarse grain texture, and fine grain texture. There is a very important connection between the rate at which rocks cool and the texture of the rock. Igneous rocks that cool slowly will tend to have larger crystals. As an example, granite is a coarse-grained rock, because it cools relatively slowly. If you look at our picture of granite, you can see these very large chunks of mineral, and you can easily identify the dark grains from the lighter grains, from the orangish grains. Those large mineral grains are present because as the granite took a long time to cool, very large mineral chunks were able to form. However, if an igneous rock cools rapidly, we'll see smaller crystals in that rock. In fact, the mineral grains can be so small you can't even see them with the naked eye. You need a microscope. A really good example to consider is rhyolite. And rhyolite is granite's extrusive rock equivalent. Both granite and rhyolite are composed of light-grained silicate minerals, but because rhyolite forms at Earth's surface, it cools much faster than granite would cool. So the rapid cooling rate of rhyolite gives it a fine grain texture, where the mineral grains are far smaller than they would be in granite. Our last consideration for this particular slide is instantaneous cooling. We're talking super rapid cooling. And if magma or lava go from a really high temperature to a really cool temperature in a very short amount of time, you will see a glassy texture for a given rock sample. I showed you a piece of obsidian in a previous video, and obsidian is a great example of an igneous rock that underwent extremely rapid cooling. And anytime you see a glassy texture for a rock, we know that we are talking about very rapid cooling for molten rock. Okay, that concludes our video overview of igneous rocks. The key point to keep in mind whenever we talk about igneous rock is that we're talking about rock that formed from either magma or lava. In our next video, we'll talk about sedimentary rock. And as you'll see, sedimentary rock forms under very different circumstances.